So what I'm going to talk about is mainly this paper. This is a famous now paper by George Sugihara, where he found a new method to detect causality, using something called Takens theorem, which I'll go into a little bit. And this, although this was done for ecology, and I did my sort of a postdoc with George Sugihara, is basically this is a method that allows you to look at things that you can find causal relationships from time series, and then you can actually find causal relationships of time series even when there is no correlation. So like what Terry was saying earlier, there are there is correlation, and then it's like people think it's causation, and many people thought that correlation and causation, some people think that correlation is necessary for causation, but later on I'll show that this is actually not the case. And a lot of I'm just gonna go over this sort of relatively briefly, because I have a lecture that is in the syllabus, and that's like more extensive about all these tools that the Sugihara lab has developed. And that's sort of like an over an hour lecture. And if there is need, I will maybe just have a separate lecture to go over this into detail, because I mean, it's a little bit involved. So I'm just going to give you a flavor of it in terms of the basic principle and also how you can use this to study neuroscience. So, okay, here we go. So one thing is like, many times that we think there's things that, especially in, biochemistry, molecular biology, these are very low throughput kind of things that they have very little data. And we assume things are static, and then we use statistics to tell us like condition 1, condition 2, and compare, see if there's a difference. But, this is actually not the reality, in the sense that, if a system is dynamic and is changing over time, if you use statistics to look at this thing, many times what you're doing is basically I take 10 frames, like this is in La Jolla Cove. These two are dynamic situations. It's like if I took 10 frames of that movie on the left that was done in the morning in La Jolla Cove, and then I take 10 frames of the movie on the right, and then do a statistical average of it, and I compare the two. This is basically the type of analysis that you're doing. It's not that there's a difference, but you're kind of missing the point. So to look at things dynamically, you actually have to look at it in a different way. So the natural way to do this is this thing called attractor reconstruction in manifolds. So this is basically the Lorentz attractor. The Lorentz attractor is defined by these 3 ODEs. And what you can see is like, this is the over time, if you throw the, if you project the, like the x-axis, and you have time moving towards you in this case, then you actually have a time series. But you can also have a time series for y, and also a time series for z. So this manifold that you actually have is the reconstruction of all 3 time series put into this object, this multi-dimensional object. So in this case, we have 3 ODEs and 3 variables. So this thing is actually in 3 dimensions. And then you can actually go between time series and, and a manifold. And from a manifold, you can also generate a time series. So if you go back and forth between those two, there's a natural way to go back and forth between these two. So one thing is like, that was very important, is this thing called Takens theorem. Although Takens theorem was actually discovered by an undergraduate at UC Davis. His name is Jim Crutchfield, and he is basically the director of the Center of Complex Systems over at UC Davis. But when he was an undergraduate in UC Santa Cruz in 1978, he actually found this thing called a Takens theorem. And then there was actually formally proven a few years later by Floris Takens. So since it was mathematically proven as a generality by Floris Takens, it carries Takens' name, although it was, discovered and first used by Jim Crutchfield. So what is this thing? So the Jim Crutchfield, being the undergraduate, he just got sandwiched in between. And this is the paper basically because it's geometry from a time series. How do you generate geometry from a time series? How can you convert a time series into geometry? And the principle is relatively easy. If you actually look at it, we had these 3 ODEs that define this Lorentz attractor, like I showed you earlier. But let's say you only have one variable, and the only variable that you have is this x variable. So if you take this x variable and then shift it over by an amount tau, and then shift it over by an amount 2 tau, so this is, all these three are like the time series of x, just as one shifted over, temporally shifted, because in this direction we have time, you're just shifting it over, and now you make them new coordinates. So you make this your new x, your new y, and your new z, and then you plot them in this, what you call phase space. And this shape, as you can see, is kind of has some similarity to this. And how it's actually similar, you see in the next video. So so the Takens theorem says that out of a single variable, you can generate a manifold that is like the original system, but just a stretched form of the other one. It's called the diffeomorphism. And here you can actually see again, this is the, the variable x, and shifted by amount of tau and shifted by amount 2 tau. So now we actually make these your new x, y, z, and then you plot them against each other in phase space, which you'll see in a minute. So as time evolves and the system evolves and it changes, you actually evolve a manifold that is basically a stretched form of the original Lorentz attractor. You can see it has 2 lobes like the original one. And for every point that exists on this, what we call now shadow manifold, this delay embedding, there's a point in the original manifold. So every point that exists in the shadow manifold exists in the original manifold. Now, so how can we actually use this? So if if you actually had a system that originally had variables x, y, and z, and variables x, y, and z were influence each other because they're coupled causally, one is causing another one to do something. And you remember that we showed that, the shadow manifold of x, or variable x, you can actually make this manifold. And then you can actually do the same thing for y. So y also has a manifold for which each point that exists in the original manifold M is also in the shadow manifold My, and also in the Mx also has the same. So for every point that exists, the other also has the equivalent point. And what is more, the nearest neighbors, so basically the neighbors to any given point in shadow manifold of X and shadow manifold Y are equivalent. So they should have the same neighbors. So if they were originally part of the same system, you can test were the neighbors preserved. If the neighbors are preserved, then you can predict where it's going to go next. So you use the neighbors to predict where it's going to be the next position. So you can predict across each other. So that means that if you actually have 2 systems where you actually can predict across each other because they share information like a cause and effect, they must also, share the topology of this so-called shadow manifold, which is made out of the delay embedding. So this is the basis of, if you can predict between these variables, that is what convergent cross-mapping is doing. So if you can predict because they share information, you know that they have a causal relationship between each other. And they may not be, correlated at any given point in time, right? So what another property is that this is convergent. So convergent means that the more data you have, the better your prediction is going to be. So for example, if you actually have, in this particular case, this is a couple system where from one side you can predict much better than the other side, and there's it converges faster. That means that with more data, you make a more dense map, and the map that is more dense will allow you to predict better. So, okay. So we can apply this to brain like that. So the system that I use is zebrafish. And here we actually look and we have embedded zebrafish, and we actually use light sheet microscopy. So the head of the fish is embedded, the tail is free. So you can actually see the movement of the tail. When you present like low oxygen, the fish tries to escape. But we can image it because we actually have GCAM6 that's localized to the nucleus that gives the calcium imaging for this thing. So This is like whole brain imaging with light sheet microscopy. And then you can actually see that every dot that you see is one nucleus, and it responds to the it responds to the calcium depolarization, the calcium change that you actually have in the cell. And then you can actually see that for these big pulses, you can actually see that the signal actually goes everywhere. So just like what Terry's saying that, like in the middle area here, this is the optic tectum. This is like the motor, the midbrain and the motor areas. It's like, how come, when you actually have motor activity, which we know that's related to the fish trying to escape, it actually shows up, in the optic tectum.
Yeah.
So you can clearly see that are coordinated, right? And that goes all the way to the forebrain. So the forebrain is like a lot of decision making is done in the forebrain. This is like similar to the human, frontal lobe or prefrontal cortex in terms of functional equivalence. You can see that also there, you can actually see some of this activity propagating. So this is basically, the brain is sharing information across really large swaths. And then basically here we can actually, using convergent cross mapping, we can actually, identify it and then see what can predict what. So when we actually take time series, like this is the sort of like the process data that you get out, you can actually get things also like embedding dimension. So embedding dimension tells you basically how many dimensions do you use to embed it. It can tell you how complex something is. So basically embedding dimension, you can roughly think as the number of inputs that are non-redundant and the number of outputs that are non-redundant combined. So for every single neuron, you can sort of count number of inputs that are non-redundant and number of outputs that are non-redundant. And all of it together will form basically the embedding dimension. So here we actually have the distribution of embedding dimensions of every single neuron in the brain of the fish. And if you actually look at under normoxic conditions, there were a whole bunch of high dimensional neurons. And then when you actually gave it the hypoxic thing, where you actually direct the task of the fish to escape, you actually see an increase in these low dimensional neurons. So you simplify the behavior. And if you plot them against each other, you see a bias towards the normoxia side. So basically this side is that normoxia is high, hypoxia is low. So this is basically the transition that we made. So this is basically the density plot of it. So if you actually look at where this thing is, so you actually see one is low dimensional, like one dimensional, and this like 20 dimensions. So you can actually see that when you go to hypoxia, that's actually an enrichment of this low dimensional things, especially in the motor areas. The visual tectum pretty much stays the same. So you can actually see here that is like, if you actually look at the transitions from which neuron was, for example, here where I go under hypoxia, this neuron was 4 dimensions, and the normoxia, it went to 2 dimensions. So going from 2 dimensions to 4 dimensions, they'll be here. So actually you just plot how many you have, and you can see the shadow, the gray shadow that you actually see here. That is the gray shadow is telling you like towards this side, telling you that under hypoxia, you lower the dimensionality of the system. So there are more neurons. So if you actually look at every single neuron, and this is basically what is like what's the preferred dimensionality of each neuron? Basically, how many inputs and outputs does it have that are non-redundant? And then actually you see like how well are these neurons predicting? You can actually see there's a bias for the high prediction skilled ones that are relatively low dimensional. So that means that, although the neurons have many inputs and many outputs at any given behavior, you seem to see the majority are not having that many. So there's actually they actually sit on these low dimensional spaces. So these low dimensional spaces also explains probably why we're finding these manifolds everywhere. So what about timescales? One thing that you can actually see is like, which is the timescale that I should use to predict best? So one thing that we see, that's expected, the vast majority of the neurons are really like fast. But as you can see, the fast ones we actually have here in yellow, and the slow ones we actually have in one. And we're looking up to about 15 seconds ahead. So like 15 seconds ahead, that means this neuron predicts its own behavior best if you use this time scale of 15 seconds. So that's an eternity for the brain, right? So you can actually see that they're scattered all over the brain. There's these low, basically slow neurons, I call, but also but the vast majority are like these fast neurons. But there's some of these, like the brain is basically working at multiple time scales and not just one. Okay, so what do we actually do the causal analysis? So if you actually look at a causal analysis on basically normoxia, and the normoxia in this guide is what is basically like what you typically call the default state, when the brain is not doing anything. So when it's not doing anything, then you let it see what are the cause and effect relationships. And here we actually pick 154 representative neurons of the entire brain, and then calculated it. And that was basically because of the computational expense of doing this. And then you can see these clusters of activity. We actually cluster these behaviors, and you can see there are like these columns and these rows. And each of these columns and rows are basically, these are patterns of input, and these are patterns of output. So the horizontal ones are like patterns of output and patterns of input, basically in terms of cause and effect. And you can see that you actually have many different clusters under these. But if you actually give a directed, so when the fish is trying to escape this low oxygen, actually everything kind of merges into one large one. So the direction, and it's basically when you actually gave the fish a directed task, basically what you actually is like you simplify the behavior and you make it only do one thing, because it only cares now at this point of getting out of this low oxygen environment. So you can actually see that the brain is much more coordinated towards a single task. Well, one thing that we can do here is basically show which are the things that are non-redundant. And then we can actually do this so-called dimensionality reduction by causal inference, which is basically we remove the irrelevant and non-redundant variables. So this way we actually, when we actually do this, and we just subtract the correlation component. Basically, correlation means that's almost identical. So it's like, what kind of things are there? They're non-identical that we actually have that are still information that are above and beyond what correlation would give you. And then it's basically, you see these nice, basically columns here and rows. So these columns that you actually see here, these are actually basically inputs. So for this particular neuron, this neuron is receiving inputs from all these other ones. And if you start clustering them on the both sides, you're gonna see, okay, these guys look very similar. So this cluster here is basically, they have almost equivalent information in this other one. And out of these, we can actually pick representative ones. And if you pick a representative one, then you can actually form a manifold of the particular neurons. And this is basically out of 3, we actually basically predicting the motor activity of the fish out of this manifold. So this is the embedding of this of a manifold of these 2 neurons with a behavioral output. So as you can see, this is the embedding and this is the activity. And when you actually see that every time that you actually have this loop coming out, that loop represents basically an escape behavior. So that's basically every time that you actually have this, you can actually predict at least half a second ahead for every case using this manifold, when a fish is going to escape, at least half a second ahead. And we actually have 2 types of escape behaviors, and those are represented here. And one of those neurons actually was found previously by David Tank in Princeton to be predictive of basically eye movement coordination. This basically sensory motor integration of visual signals. So anyway, so we actually, in order to scale this up, we initially had to use a supercomputer to do this. And we used world's number 7 fastest supercomputer at the time. And now it was number 7 when we started, now it's number 15. And then this is basically the causal relationship of an entire brain at single neural resolution. So you can actually see the left side is the hypoxia one, and the right side is the left side is hypoxia one, and the right side is normoxia. And actually, as you can see, the normoxia, everything is much more connected. The information, basically the signal that you actually have, the yellowness of the whole thing is increased, and is increased across the entire thing. So basically, this actually tells you that pretty much every part of the brain has some information leakage to the other part of the brain, and is very, very wide scale. There are very few places where there's actually no information. And that if you actually have like, and it's much more segmented in the default state than in the sort of when you actually have a goal-directed state. So, okay, so I mean, this is all nice, and this is sort of observational. Can we go beyond that? Can we actually make something that allows you to basically, as we all know, that can we actually make predictions, or can we actually generate a model that actually goes beyond that? And that we actually did is basically like, can we actually, we want to do is develop methodology to download the brain activity using these convergent cross mapping. So you can reproduce a realistic brain activity as well behavioral outputs in a computer simulation or robotic embodiment. So that's basically what we want to make. Can we download the brain and using just this information, not actually making the physical connectome, but just basically the information relationships, and get something out that actually behaves like a real one. So what we use is like data from Sophie, who used to be in Terry's lab and also Graham Greenspan's lab. And here, basically, you're using light field microscopy to look at brain activity. And at the same time, what is really nice, you actually have it on basically on the trackball, on a styrofoam ball. We can actually record the movements of the fly. So here, basically, what you see is basically, this is like you had this, the ROIs, basically the regions of interest across the entire brain. You don't go quite as single neural resolution, but they're like basically about 80 areas that are, and then it's basically you try to see, can these areas predict the movement? Can we map the basically the activity of the brain to the movement of the fly in terms of forward speed and left-right speed? And here's basically an example of the manifold that you actually generate. This is a univariate manifold of the activity in the fly brain, and you can see it forms manifolds. And basically this is the dimensionality, the distribution of dimensionality. We don't see anything that is linear. So basically, like, just things that are with the best prediction is like just purely, a linear fit, like a linear correlation, you see nothing. So basically all the things are better for a nonlinear prediction than is like, and the majority of them are in this sort of low dimensional space between 4 and 7 dimensions, not more. And if you actually cluster them, you can actually see that if you were to represent the entire brain in terms of all these are inputs, the vertical arrows, and outputs are this. So basically there's seem to be 3 main types of outputs, and they're about, approximately, 5 types of inputs for this thing. So then we actually do a dimensional reduction, and we actually do, basically we subtract them from correlation to remove the non-redundant things. So basically we just, what I call non-linear residual, the residuals define the non-redundant information, so we can actually choose these things. And out of the members that we actually choose here in the sparse matrix that you get, we actually generate individual manifolds that predict, another neuron or movement. In this case, basically forward movement or left-right movement. And we actually can combine it into a manifold that predicts both left-right movement and forward movement. So what you get out of that, basically, when you make this, you actually generate basically a network of manifolds. And then finally, you predict the left-right regressors and the forward regressors, basically left, right, and forward. So you have the entire brain made into a network of manifolds trying to predict left, right, and forward movements. And how well do we do? So if you actually were to use the best neuron that we have to predict forward movements, and this is basically the forward speed that you see over time, and this is like 0 time to time point 600, and then you just keep predicting from there. And then you try to use a manifold to predict what it's going to do next. And then you take the result and throw it in, and then you try to predict the next step. And then based on assuming that your prediction was correct, you predict on and on, but you get into this thing that this thing dies off. However, if you make it a neural network, you can get things that look like they behave more or less normally. They look kind of realistic. If you actually do that, that was the forward movement. This is basically neural activity of that same neuron. This was basically the real data that we use. And then it starts to predict, generated data. This is basically imagined data by the model. And it looks, fairly realistic. And if you actually look at the, let's say the forward movement using the entire brain information to see, and you do a Fourier transform of it, it actually looks pretty similar. The correlation coefficient of the real observed spectrum of movements, the forward movements, and the manifold network, basically represented ones, is 0.92. So it's not bad. So here is basically, you have the left-right speed. This is basically the phase portrait of the movement of the fly, and this is the real movement. And then if we use the manifold network, this is the shape, this is the speeds, left-right speeds, and the forward speeds that you actually have. And then we actually try to see, is the brain information important to generate this? So we leave the brain information and just take the historical movement information and do an embedding of that and use the movement itself to predict movement. It actually doesn't do very well. It's not very realistic. So you can actually see that the behaviors in the real one and the brain information is important for predicting future movements and simulating movements. So if you actually look at, for example, the components individually, this is basically the forward speed from the training set, and this is the predictions that you actually have. This is the observed ones, and this is basically the generated manifold network. This is the total of the real data, and this is the manifold network. I mean, of course, it's not going to be exactly the same because it just has to have the same character, and then. But if you actually look at the movement along and do an embedding of the movements along, it doesn't look nearly as this, and especially this one, it dies off. So the left, right, it dies off. So the other way you can actually do an embedding of all the data. So basically not make a network, but just make one manifold of 80 dimensions where you actually have everything. And then it becomes this repetitive motion that goes on forever. So that one's also not as realistic as the other one. So if you actually look at the true data left, right, this is the generated manifold network. This is another left, right, and forward alone. And this is what we call the flattened network. This is basically like taking everything. And then this is basically a linear model. So in all cases, I think the most similar one is this manifold network that we actually generate. So to test in the end is like how good this thing is in the end. We can actually say like, okay, can we actually, to have basically a better metric, we say like, okay, we're going to generate this artificial data from this network. And then we're going to see, can this artificial generated data predict real withheld data? And that's what we're trying out. And when you actually do this, you can compare to the other models. That's the blue line. And for almost every single neuron, except this one, for example, is like this generated manifold network approach works better than the other ones. And what really surprising is that, for example, when we actually generate this is the real data, and we use this blue part here as a training set. And then there was a period where the fly actually paused. This thing was not in the training set, but somehow the generated data has these pauses. So it seems that although we did not put this in the training set, this thing is able to capture certain things that exist in the brain in there. So anyway, so that's pretty much it. And the point of this is that we eventually want to put this into something like a robot for the fish at single neural resolution, where the robotic fish will actually be controlled by the simulation of a real brain of a real zebrafish. And then Also, we want to have a learning algorithm for this. Anyway, that's pretty much it.